Hello guys. Good morning. I hope everything is all right now. You can hear me properly. Good morning. I hope everything. Just confirm if everything is all right. So today in this session we'll be discussing particle in a finite symmetric potential well. Symmetric is finite potential box. Okay, symmetric. Yeah, can also say that. So basically particle in a finite square well potential box. So we have seen in the previous cases that the potential was infinite. So under no situation particle was able to come out of the potential box. But now in this case, in case of finite square well potential, the potential is not infinite. So it is like this. So one thing is clear, that if the potential is not infinite, it means the wave function will not vanish in region 1 and in region 2. Okay. So we can imagine that the height of this potential here is V naught. Obviously this will be V naught. Now this is 0, this is plus A by 2, this is minus A by 2. So the width is A. Now we are dividing it into 3 regions. One is this region, second one inside this box, third one is this. Okay. We have already done similar steps, so I will be jumping some steps while doing this calculation. So this is a one-dimensional finite square well potential box. Why it is finite? Because the potential is are not infinite. It is finite value, having finite value of V naught. This is V naught. So how do we define the potential? The finite square well potential is defined as, you see, V of x, this is 0 in the range minus A by 2 to plus A by 2, and it is V0 otherwise. Otherwise means we can also specify that when x is less than minus A by 2 or when x greater than A by 2. This is what otherwise means here. Now there may be two solutions. One may be, let's say a particle is there inside this box. So the particle's energy may be greater than V naught. So when the particle's energy E is more than V naught, so this will give rise to scattering state, scattering states, scattering case. So that is not our concern. Our main concern is to calculate bound state. Bound state, because for bound state we will get discrete energies. Bound state corresponds to when your energy, particle's energy, lies between 0 and the height of the potential. Okay, this will give rise to the bound state. So for bound state we will be doing the solution. Good morning Murli, Harry. So you see, for the bound state, if you find the solution, we can use the Schrodinger equation. So we can use the Schrodinger equation in different regions. Minus h cut square by 2m d square psi by dx square plus v of x psi is equals to e psi. Okay. So first of all, if I talk about this first region, region 1. So that is x less than minus a by 2. So for this region, what will be the solution? For x less than minus a by 2, you see the potential is V naught, okay, V of x is equals to V naught. So this Schrodinger equation becomes minus h cut square by 2m d square psi by dx square plus V naught psi is equals to E naught. So what we can write? We can write d square psi by dx square. Now we have to choose in such a way that the k value should be positive, okay. So here let us say instead of k will be using for this mid portion. So we are writing, we could have written k1 k2, but for the timing we are writing gamma in place of k. So gamma is equals to square root of twice m. Look, here the energy is less than V naught, so obviously this will be V naught minus E. Okay, if you do E minus V naught, because E is less, then this term will be negative and that will be imaginary, but gamma cannot be imaginary. Twice m V naught minus E by h cut square. So we have to write the equation in such a way that you get this twice m V naught minus E. But if you take twice this thing on the other side, and if you take it to this side, it will come out as plus. So what we can do, we can write minus, okay, minus twice m V naught minus E by h cut square psi equals to 0. Can I write it? And that makes the equation d square psi by dx square minus gamma square psi equals to 0. So this will give you the characteristic roots to be plus minus gamma, and as a result of that we can write the solution in this way. I am writing in the terms of phi, okay, although we have written in terms of psi. So psi is equals to, let us say, a e to the power gamma x plus, let us say, b prime e to the power minus gamma x. Why we are not taking b? Because this is going to be vanished somehow. Look, psi, this is a solution. So to denote this wave function as the wave function of the region 1, we are alternatively we are expressing this as phi 1, okay, wave function in the first region, phi 1 a to the power gamma x plus b prime e to the power minus gamma x, okay. Now we are using the boundary condition. What is the boundary condition? That we have told you the property of wave function, that the wave function must vanish at x equals to plus minus infinity. Now you see, since the wave function must vanish at x is equals to x tends to minus infinity. So does it mean particle can also exist outside the well even though its energy is less than V naught? No, no, in that case it will be giving rise to tunneling, okay, na? Simple. If the particle's energy is more than V naught, then it can come out the way we see classical things, scattering problems. Now when the particle's energy is less than V naught, classically it is not possible for the particle to come out, but quantum mechanically there is a probability to find the particle in the other two regions. So obviously that will give rise to tunneling. The particle can exist theoretically with the help of tunneling. So if you consider the wave functions, it will be exponentially decaying like this. Got it? Since the wave function must vanish at x equals to minus infinity, what you can write? If you see, if you put x equals to minus infinity, this term diverges. But if you put x equals to minus infinity, this term follows this property. Since the wave function must vanish at x equals to infinity, and for x tends to minus infinity, the second term of phi 1 blows up, hence b prime is equals to 0. So if b prime is equals to 0, we can write the wave function of the in the first region is equals to a e to the power gamma x. Clear? So this is the first region we have calculated. Let's go for the second region when minus a by 2 less equals to x less equals to plus a by 2. Sure. Less equals to I should not give here. In fact, I should give it here. X less equals to minus a by 2. So for this region, what we will have here, you see the potential v of x is equals to 0. So your minus h cut square by 2m d square psi by dx square plus 0 is equals to e psi. So as simple as that, d square psi by dx square plus we can simply write twice m e by h cut square psi equals to 0. Now if I take square root of twice m e by h cut square as k square, I can write it in this way, where this k is equals to square root of twice m e by h cut square. So this will give rise to the solution psi is equals to, you see, b e to the power I k x plus c e to the power minus I k x. Following the trend, we can just write the wave function in region 2 is equals to b e to the power I k x plus c e to the power minus I k x. So one more region is left, that is x greater equals to a by 2. So it will be similar to what we have observed in case of, in first case, only here the second term vanished, here it will, the first term that will vanish, because wave function now, you see, if you consider the region 1 is, let's say it is starting from here, so it is going along this direction, so it is ending at minus infinity. If you are considering region 3, it will be ending at x equals to plus infinity. So we have to check whether the wave function is vanished at x equals to plus infinity. Okay. So for x greater equals to a by 2, here also you see v of x is equals to v naught, and what we can write? We can write same. Okay, I am not showing you the whole calculation because we have already shown you. So what will be phi 3? Phi 3 is equals to, let's say a, b, c we have taken, d prime e to the power gamma x plus d e to the power minus gamma x. Similar logic, since the wave function must vanish at x tends to plus infinity, and d prime e to the power gamma x blows up at x tends to plus infinity. Obviously, if you put x equals to plus infinity, this term diverges, but if you put x equals to plus infinity, it is attenuating, right? So we can write that d prime is equals to 0, and hence phi 3 is equals to d e to the power minus gamma x. Is it clear, everyone? Till now everything is all right. So we have got the wave function in the all the regions. Karthik, Harry, Murli, everything is all right till now. Now you see what we have called finite symmetric potential well. This is symmetric potential well. You can see 0 is lying in the midway with plus minus a by 2. So this is a finite symmetric potential well, potential box or potential well. So obviously if it is a symmetric potential box, it will give rise to the usual even parity or odd parity. Okay. So you see, since the potential is symmetric about x equals to 0, hence parity must be conserved, and that is why we'll deal with different parities. First of all, we'll go for even parity. So for even parity, what do you observe? For even parity, if I consider region 2, in region 2, so region 2 is the most important where the particle is lying. In region 2, we can say if it is even, so that means phi 2 of minus x is equals to phi 2 of x. Can I write? Because the symmetric thing is there in region 2. As you can see, this is the region we are talking about. So phi 2 of minus x is equals to phi 2 of x. So if you utilize this, then what you can write? Phi 2 of minus x. Phi 2 we have got b to the power ikx plus c to the power minus ikx. So b e to the power minus ikx plus c e to the power plus ikx. We have put, so b e to the power plus ikx plus c to the power minus ikx. Right? Now, under what condition it is possible? Just look at it. B here e to the power minus ikx, here e to the power minus ikx, here but it is c here. E to the power ikx, e to the power, acha. Look, e to the power ikx, e to the power ikx, but here it is b, it is c. So under what condition this equation will be hold? Obviously when b and c are equal. Can you write region to a function trigonometrically? No, here instead of writing trigonometrically, this will be suitable for us. Obviously you can write, it can be expressed in terms of sine and cos, no issue in that, same thing, but here keeping exponential will be suitable for us. So under which condition this is possible? Only when b is equals to c. So b is equals to c, so we can write now the wave function in region 2 it becomes look, e to the power I kx. You will understand the reason why we are not keeping it in terms of sin and cos. Now because you see b and c becomes equal, so we can write it in this way. Okay, so it becomes 2b, b and c are equal, so I am just writing it by taking b common. Now if you want to express it in terms of sin or cos, let's say multiplying by 2, dividing by 2, so this become cos, and 2b, let's take another constant, E is not energy, E is some constant here. Remember, this is not energy, it is just a constant. So phi 2x is equals to E cos kx. Now you see, since the wave function is continuous, right? Continuous. So it must be continuous at the boundary. We can write, you see, whatever wave function expression will be here. Now when you are going to this boundary, so wave function is not like discrete, like it is not like this, then it is starting from here, it is continuous, right? So if you check the value at the boundary with the same form, if you check the value at the boundary, if either you put the formula of phi 2x or phi 3x, that will match, that will be same, because we are calculating at a fixed point, right? So the property that the wave function is continuous at the boundary and its first derivative is also continuous at the boundary. So what we can write, you see, phi 2 at x is equals to plus a by 2 is equals to phi 3 at x equals to plus a by 2. Can you write? So if you write it, x is equals to plus a by 2, so E cos k by 2 is equals to phi 3 was what? It was d to the power minus gamma x, d e to the power minus gamma x is a by 2. Wave function is continuous at the boundary, continuous, and also write and differentiable. At the boundary. So this is for the continuous condition. What about the differentiability? D phi 2 by dx at where x is equals to plus a by 2. It must be equals to d phi 3 by dx at x is equals to plus a by 2. Okay. So what we can write? Derivative of E cos kx, so Ek minus Ek sin kx, x is equals to a by 2. This is equals to d to the power minus gamma x, d to the power minus gamma x. What is the derivative? Minus gamma d, minus gamma d e to the power minus gamma x, x is equals to a by 2. Okay, so let's call it equation number 1 and equation number 2. What will happen if you do 2 by 1? Dividing equation 2 by equation 1. What you gonna get? Sin k by 2 by cos k by 2. That is tan k by 2. E get cancelled. So minus k, and minus minus this plus, minus minus is cancelling. So there is no sign of minus. It is k tan k by 2 is equals to dd get cancelled. So gamma d e to the power minus gamma a by 2. Acha, e to the power minus gamma a by 2 is also cancelling, right? D is also cancelling. So it will be like this. K tan k by 2 is equals to gamma. Now you see here k a by 2 is there, here only k is there. So what if you multiply sorry guys, a by 2 on both sides? So we have multiplied a by 2 here, so gamma along with a by 2 we have multiplied on both sides. Now what we are doing, we are defining two terms. One is eta, let's say gamma a by 2, and this xi is equals to k by 2. If we define these two terms, what will it become? Ka by 2 is xi tan xi, then this is tan xi is equals to gamma a by 2 is equals to eta. So eta is equals to xi tan xi. Is it clear or not? क्या बोल रहे हो? By 2 missing left side of equation 2. Where? Where it is missing, I can find, Murli. E cos kx was there, so minus ek sin kx, so x equals to a by 2. Here d to the power minus gamma x, so minus gamma d e to the power minus gamma x equals to a by 2. Nothing is missing, I think. Just cross verify. Now eta is equals to xi tan xi, and as you can see from here, eta is equals to gamma a by 2, xi is equals to k by 2. So we can write eta square plus xi square is equals to square of these two and add. So a by 2 is common, so a square by 4 gamma square plus k square. Now you see eta square plus xi square, gamma square plus k square. What is the value of gamma square plus k square? Gamma square plus k square. Gamma we have got twice m v naught minus e upon h cut square, and k is twice m e by h cut square. So this is twice m v naught by h cut square, and that makes eta square plus xi square is equals to a square by 4 into gamma square plus k square, a square by 4 into twice m v naught by h cut square, that is m v naught a square by 2 h cut square, right? So this is nothing but the equation of a circle, right? So we can write eta square plus xi square is equals to r square, where r is nothing but square root of m v naught a square by 2 h cut square, isn't it? So we have got two equations. One is this equation, another one is this. Now we need to find out what are the even bound state energies. So to do that, we have to solve these two equations, this equation and this equation. Now you see, solving these two equations algebraically is not possible. So either you have to go numerically or you have to do it graphically. Okay. So the even bound state energy can be found by the solution of equations. Firstly, you see eta square plus xi square is equals to r square. R is square root of twice square root m v naught a square by 2 h cut square, and eta is equals to xi tan xi. How? Graphically. Okay. So how to find this solution graphically? Try to understand. This part is very crucial and a little bit maybe it may appear to be a little bit difficult for you to understand, but if you go step by step, then it will be easy for you. So if you are given two equations and if you are asked to find out the solution, how do you get the solution? You plot the two equations, right? And whatever be the intersection point or the cutting point of those two equations, that gives you the solution, right? Here also, this is the equation of a circle. This is the equation of a circle, and you know eta is equals to xi tan xi, how it looks. So first of all, eta is equals to xi tan xi will plot. Okay. So the values may be considered at pi by 2, pi, 3 pi by 2, 2 pi, and so on. So we are plotting eta along y axis and maybe xi along x axis. So this is 0, this is pi by 2, pi, 3 pi by 2, 2 pi, and so on. Is it a straight line equation? Which one? Eta is equals to xi tan xi. Look, actually there are three equations. This eta is equals to xi tan xi, eta is equals to xi tan xi. This is one equation. Another, eta square plus epsilon, sorry, xi square is equals to r square. This is a circle. It is tan function, and you know how it looks. So let's first plot the tan function. So tan function, you know how it looks like. it looks like this, right? It will look like this. This one which we are doing for even bound state, okay, for even bound state, remember this thing, this you must keep in mind, everything under this calculation comes under even bound state. By assuming this thing, psi 2 of minus x is equals to psi 2 of x. If you consider psi 2 of minus x is equals to minus psi 2 x, that will be for odd parity and everything will change, okay. So this is for even bound state. So this is for even bound state. So we have plotted eta is equals to xi tan xi. Now how is this eta square plus xi square is equals to r square? This is concentric circle. The way you choose r, okay, it is like, you can imagine it in this way. If you put some radius which is between 0 to pi by 2, so any value you can draw like this, you can draw like this, or maximum you can draw like this, right? So we are not showing every portion of it, we will just show a small portion, like let's say a circle we have here like this. So we will only show this part, okay. So you can imagine that it is a circle like this, but for our convenience we are showing only this part, okay. So when the radius is between 0 to pi by 2, so you can draw like this, okay, sorry, up to you can draw like this. So I'm just drawing it, maybe any radius between 0 to pi by 2, so it will be like this, okay. So you can see it is cutting it at one point. Now we can choose other radius also, okay. If your radius is between pi to 2 pi, then any pi to 2 pi, then any radius, maybe any circle may be drawn like this, and accordingly it will cut. Now let's name this, look, this is n is equals to 0, this is n is equals to 1, 2, 3 and so on. So we are only interested in the even bound state. So this is the first one, 0, even. This is not the quantum number, it is another thing, okay. So this is even, this is even, and this is even, and the next one will be even. Here whatever it will come, that will be even. So for odd, n equals to 1 is what, n is equals to 3 is what. So for the time being we are denoting it by dotted line. Just to differentiate it with the even. So wherever this even line are getting cut, that will be the solution, okay. So when the radius is 0 to pi, okay, 0 to pi, so at how many points it will cut? In between 0 to pi, you see how many even bound state will be cut. Whether you take radius like this, it is cutting at one point. Here if you take, it is also cutting at one point. Even if you take radius more than pi by 2, then also it is cutting at one point, and with pi also it is cutting at one point. 1 point means one bound state. So when you restrict your radius between 0 to pi, you get one even solution, okay. For the timing we are considering only even, so odd we are not considering, but obviously one odd will be added here. When you take the radius between pi to 2 pi. Okay, more than pi, less than 2 pi. So it will cut at n equals to 0 and n equals to 2. Okay, let's say we are taking something like this. So as you can see, it is cutting at n equals to 0. Obviously n equals to 1 it is cutting, so one odd bound state is also there. N equals to 2 it is cutting, n equals to 3 is also cutting. So you can see 2 even, 2 odd. But for the timing we are focusing only on the even. So you imagine the circle like this. It is the circle like this, Okay, it is covering the whole one. So when you keep your radius between pi to 2 pi, how many even solution you get? You get 2 even solutions. And when you choose your radius between 2 pi to 3 pi, so you will get 3 even solutions. Is it getting clear or not? So this is for even bound state. So in a similar manner, you can proceed with the calculation for odd parity, right? Look here, I would like to mention one thing. R is equals to, R is equals to square root of m v naught a square by 2h square, right? Here this m v naught a square by 2h square root, that gives you R. So here this v naught a square, this is known as the strength of the potential. Strength of potential. Not start from 2 pi. Yeah, it can go up to less than 2 pi. Okay, it is, you can see, less than 2 pi. Whatever radius means what? This is the radius. Okay, so if you are choosing something, any value between this, it is 0 to pi by 2, this is radius. When you are choosing between pi and 2 pi, any radius between pi and 2 pi, so it may be minimum this much, maximum this much. In between we have taken this. Pi to 2 pi means any radius, any circle will work. Even if you take this, it is cutting at 2 points. You take 2 point, you take 2 even, up to 2 pi it is again cutting 2 pi. Now if you proceed with this similar calculation with odd parity, for odd parity what we have to write? We have to write psi 2 of phi 2 of minus x is equals to minus phi 2 of x. And if you apply all those boundary conditions, the wave function is vanishing at the boundary and its first derivative is also vanishing at the boundary. Using that, you will get eta is equals to minus xi quad xi. Okay, and eta square plus xi square. Here we get eta square plus xi square is equals to r square, where r is again square root of m v naught a square by 2h cut square, and instead of eta is equals to xi tan xi, here you will be getting eta is equals to minus xi quad xi. The plot will be similar. Okay, so let's just copy paste this image only. So we are only interested in knowing the even and odd bound state. So I am doing it for now odd bound state. So for odd bound state, which one we will be considering? n is equals to 1 and n equals to 3. So n is equals to 1 and 3 we are drawing with solid lines. One and 3, and for 0 and 2 we will draw with dotted line. Now if you choose radius between 0 to pi by 2, will there be any odd bound state, like any radius between 0 to pi by 2? So you see it is not cutting n equals to 1. So when you are considering radius between 0 to pi by 2, 0 odd solution, no odd bound state, you can say no odd bound state. When you choose a radius between pi by 2 to pi by 2 to pi, so what will you get? Pi by 2 to pi. So you can see it is cutting at one point. So one odd bound state, and obviously one even bound state is also included here. Now when you choose your radius between pi to 3 pi by 2, how many odd bound state will be there? How many odd bound state will be there? Pi to 3 pi by 2. So you will take a radius like this. Like this. So it is cutting at only one point. Here also one odd bound state. Now if in your examination, in the question, if there is nothing mentioned whether it is even or odd, then what you can write? In general if you look for it, let's say for this complete figure, not even or odd, okay, let's say we have an image in general between, if you take the radius 0 to pi by 2, okay, 0 to pi by 2, 0 to pi by 2. So you can see it is having only one even bound state. Let's say between pi by 2 to pi, pi by 2 to pi means, let's say something like this. So it is cutting at one even, one odd. So it has one even solution and one odd bound states. Okay, let's say between pi to 3 pi by 2, here pi to 3 pi by 2. So you can see it is cutting here, it is cutting here, it is getting here. So n is equals to 0 even, n equals to 1 odd, n equals to 2 even. So 2 even and 1 odd bound states. Now we can easily define, even if you don't give this equal sign, that will also do your job. It will be same. Let's say I am considering, if in your examination if it asks you what is the potential condition so that there is one even and one odd. So let's say the condition, you know, it is pi by 2 less than or less than pi. For this there will be one even and one odd. Okay. So you can see pi by 2 is less than r is equals to square root of m v naught a square by 2 h cut square, isn't it? So what does it mean? If you take a square on both sides, you can see it is pi square by 4 less than m v naught a square by 2 h cut square less than pi square. So what we can write? We can write, we want to just keep this v naught a square. Okay. So 2 h cut square by m is multiplied here, 2 h cut square by m. So pi square by pi square h cut square by 2m we can write. Here pi square h cut square by m. So if you want to write 2, so it will be 4. Can I write it? Just an example. So what is the condition that there will be one even and one odd? The condition that v naught a square should be between pi square h cut square by 2m and 4 pi square h cut square by 2m. I hope this is clear. Any question if you have, you can ask. If there is no question, let's move on. Let me give you a problem similar to this. A potential is given of the form, let's say v of x is equals to infinity for x less equals to 0, it is equals to 0 between 0 to a, and it is v0 for x greater equals to a. For 0 less than e less than v naught, find the condition such that there is only one bound state. Okay. So your options may be given like this: v naught, pi square h cut square, v naught a square. Actually strength of the potential, we can calculate strength of the potential v naught a square, is equals to pi square h cut square by 2m v naught pi square h cut square by 4m v naught pi square h cut square by 8m maybe v naught a square pi square h cut square by 10m. Okay, so how to solve this particular problem? First of all, if you look at this potential, what you can write? Let's draw the potential first. For x less equals to 0, it is in infinity. Between 0 to a, it is 0, and between when it is more than a, it is v naught. So the potential is looking like this. It is infinity when x less equals to 0. Between x equals to 0 to a, it is 0, and between for x greater than a, it is v naught. So potential like this. So here also you will get 3 regions, 1 region, 2, and this is 3. So here you see in region 1 potential is infinity. What does it mean? What will be the wave function? Phi 1. Potential is infinity means the wave function must vanish. Here the potential is infinity, so wave function must vanish. What will be phi 2? So you see here v equals to 0. So we get that sinusoidal solution a to the power ikx plus b to the power minus ikx. I am just writing, okay, you already know how to write this thing. This is phi 2. And what about phi 3? Here it is v naught. Okay, and you see at x equals to plus infinity, it should vanish. So which one will have e to the power minus gamma x? Okay, you can easily connect. So we have got the wave function for these 3 regions. So here this k is nothing but square root of twice me by h cut square, and gamma, you know, square root of twice me v naught minus e by h cut square. Can you write it directly? Just tell me. Now we can use the boundary condition. We can use the boundary condition. What is the boundary condition? The wave function is continuous and differentiable. So look, phi 1 at x equals to 0 is 0. So that is why phi 2 at x equals to 0 should also be 0. So a plus b. Sure. Are you able to follow this? Tell me, Mulli, Harry, Karthik, are you able to follow this? This is equals to 0. That means a is equals to minus b. If a is equals to minus b, hence your phi 2 becomes, you see, a equals to minus b. So we can write a e to the power ikx minus e to the power minus ikx. So minus is there, so you cannot write only 2. The 2, if it had plus, then you can write 2 to make it cos, but here it is minus, so we have to write 2i. 2i you have multiplied, so we have 2i we have divided, so 2i you have to multiply. So this is sin kx, so 2i into a sin kx, 2i into a some another constant, let's say that is d sin kx. So phi 2 is equals to d sin kx. Now we can use another condition, like phi 2 and phi 3 is also continuous. So phi 2 at x is equals to a, it must be equals to phi 3 at x equals to a. Try to understand. Here the wave function is continuous, so phi 1 of 0 at phi 2 is equals to phi 2 at 0. Here also on boundary, so phi 2 at x equals to a should be phi 3 at x equals to a. Clear? So if it is so, what we can write? Phi 2 at x equals to a, so d sin k is equals to phi 3 at x equals to a. Phi 3 is c to the power minus gamma x, so c to the power minus gamma a. Now we got two equations. How? This is one equation, and the differentiability, what is that? D phi 3 d phi 2. Got space issue. So this is the continuity condition. What is the differentiability condition? D phi 2 by dx at x is equals to a, it should be d phi 3 by dx at x is equals to a. So d phi 2 by dx at x equals to a, so d, so kd cos kx, okay, kd cos kx is equals to a. D phi 3 by dx, so minus c gamma e to the power gamma x, so minus c gamma e to the power minus gamma x is a. Now we again got two equations. This is one equation, this is another equation. Okay. Now to make it so we can do 2 by 1, then you will get what? Okay. So if you do 2 by 1, what you gonna get? Cos by sine, cot, k cot k is equals to minus gamma. अच्छा, यहाँ पे हम लोग को छूट सी छूटा है ना, so gamma we are writing first. Gamma is equals to k cot k. Let's multiply a on both sides. So gamma a is equals to ka cot k. So gamma a is equals to, let's say, eta. Okay, so we can write little bit of space issue, you can try to adjust. Gamma is equals to, there will be a minus also, here also a minus, minus xi what xi, where this eta value we know, eta is equals to gamma a and xi is equals to ka. Look, I don't have space here, so I am just writing here eta is equals to gamma a and xi is equals to ka. So you see, what is the value of eta square plus xi square? Eta square plus, ultimately we require this eta square plus xi square, that will give you r. So it is nothing but gamma square plus k square times a square. Now gamma square plus k square, you can see gamma square plus k square is twice m, it can twice m v naught by h cut square. isn't it? So twice m v naught a square by h cut square, and this is equals to r square. So you see, what for one bound state, what was the condition for one bound state? You see, it should be between 0 to pi by 2. So you can take pi by 2, okay, for one bound state. So r is equals to, I'm writing it here, r is equals to square root of twice m v naught a square upon h cut square. Okay. Now you see, for one bound state, r we can take to be pi by 2, right? So twice m v naught a square by h cut square is equals to pi square by 4, and therefore v naught a square is equals to pi square h cut square by 8m a square, and that is matching with a square. Why you are writing twice? Option 3. Is it clear or not? You see, a little bit clumsy, but I think everything is all clear. Harry, Mulli, Karthik, is there any confusion? You can let me know. Otherwise, let's do this last problem for today. Similar problem. A particle of mass m is interacted with finite squirrel potential of strength v naught L square. Okay. V naught L square, where v naught is the height of the well, L is the width of the well, which is symmetric about x equals to 0. What will be the strength of the well such that there is maximum 2 odd eigenfunction exist? 2 odd eigenfunction exist. Look, the particle finite squirrel potential is symmetric about x equals to 0. So this is our first case, isn't it? The case which is given to you is this. V naught, it is symmetric about x is equals to 0, and the width is L. So it is minus L by 2 to plus L by 2. So this width is L. This is the case. So 2 odd eigenfunctions will exist. So under which condition 2 odd eigenfunctions are there? One even, one odd, 2 odd. You see, to draw 2 odd, let's draw this to get the condition of 2 odd solutions. So eta and xi 0, okay, 0, pi by 2, pi, 3 pi by 2, 2 pi, and so on. Zero, pi by 2, pi, 3 pi by 2, 2 pi, 5 pi by 2, 3 pi. Okay. Now let's draw this. Here n is equals to 0 will come, so that is we are interested in what? Odd wave function. So n is equals to 0 is what? N is equals to 1 is even. Okay, sorry, n equals to 1 is odd. So n is equals to 1, n equals to 2 is even, so n is equals to 3 will take, then n is equals to 5. And if you want to draw this, also draw look, so this is equal, n is equals to 0, n is equals to 2, n is equals to 4, n is equals to 6, and this is n is equals to 1, n is equals to 3, n is equals to 5. So we have to find out that, so that the odd bound state is 2 minimum. So which one will you take? Look, it should be more than 3 pi by 2, because if you take up to 3 pi by 2, you see it is cutting at only one point. But if you, as soon as you cross 3 pi by 2, it is cutting at 2 odd solutions. So obviously we have to take more than 3 pi by 2 and less than 2 pi maybe. So any value between this to this will do your job. 2 bound state, odd bound state. There is maximum 2 odd eigenfunction exist. So we have to take between 3 pi by 2 to 2 pi. Then we will get 2 odd. So at least there will be total 4 states. If there are total 4 states, then 2 will be what? Is it still lagging, Harry? Look, we have seen total 4 states, 2 even, 1 what? So if you go beyond 3 pi by 2, then you will get 2 odd state. So you have to find out the minimum condition, right? Maximum 2 odd eigen state will exist. 2 odd state means there must be at least 4 states in total. Hence, R should lie between 3 pi by 2 and 2 pi. Okay, R should lie between 3 pi by 2 and 2 pi. R is equals to, we know, m v naught L square by 2 h cut square. So in the question, you see v naught L square condition is given. So let's extract that. V naught L square is equals to 2 h cut square R square by m. Now R is lying between 3 pi by 2 and 2 pi. So when R is equals to 3 pi by 2, so V naught L square is equals to 2 h cut square R square by okay. अच्छा, टू h cut square by m, R square means 9 pi square by 4. So this is how much? 9 pi square h car 2 square by 2m, and for this V naught L square is 2 h car 2 square by m 4 pi square. Now if you want to write in terms of 2m, then what you can write? So this is 8 pi square h car 2 square by m. So if you want to write 16, if you want to write 2m in the denominator, so you have to multiply 2, so 8 into 2, 16 pi square h car 2 square by 2m. So we can say that for 3 by 2 it is 9 pi square h car 2 square by 2m less than V naught L square less than 16 pi square h car 2 square by 2m. So this is matching with option C. Yes, Harry. So I hope you have understood this finite squirrel potential. Look, this is not difficult. It's just that you need to understand in a systematic way. If you go through books, then you might get confused, but I think after this lecture there will be no confusion. Okay, so we are stopping here, guys. Thank you very much for joining this session. We will be discussing harmonic oscillator in the next class. Okay, bye bye, take care.